Any questions? All right. So there was a bit that I talked about on Friday, which I didn't actually do in class, so it's not actually on the recording. So I just want to put this up here for the record, that you know that the speed of a wave is equal to try that again. Speed of the wave is equal to the frequency times the wavelength, and this is for any sort of harmonic wave. And then if specifically you're talking about the speed of a wave going through a medium, then we generically have some sort of force term or a restoration term. It's how much one part of a medium will influence the next part of the medium, divided by some inertial term. In other words, how much mass do we actually need to move as we are moving things? And so specifically, for things traveling along a line or something incredibly skinny, we end up with that force term is tension, and the inertial term is linear density. Which is the mass divided by length. And so I just wanted to get that into the recording. But that was the basis of what we did on Friday. All right, any questions before we talk about Doppler effect? All right, I'm going to draw a series of pictures here that no doubt will be so incredibly good that you will know exactly what they are representing, but just in case, I will try to explain as I go. So that's going to represent something that's giving off a sound. If you need something more sensorial, let's just say every period it's giving off a beep. So this would be time is equal to 0. Now this object's not moving. This is just sort of the next frame in the comic strip here. This is at time is equal to whatever the period is. It's giving off another beep. Now the first beep that it gave off, that sound wave has already started moving out. So this gives off a beep here, which is now, and I'm going to try to center that a little bit better. Excuse my back. So this object hasn't moved. That green circle there represents the pressure wave that's created by the first beep, the one that was given off at time is equal to t is equal to 0 seconds. Trying to maintain some sort of color coordination. So that's the beep given off there. Now that sound is still moving out. So we have that first one that's moving out a certain distance here. So that first sound wave that's given off has now gotten bigger because it's expanding outwards. That second sound wave that's given off, this blue dot here, that has expanded out. And there's a third sound wave about to be created. And those circles are supposed to be concentric, even though they're not necessarily drawn that way. I'm going to try to redraw the green one a little bit better. And I'm not convinced that is. But this would be one period later, so 2 times whatever the period is. If you need something more concrete, just picture every second it's giving off a beep. And then the last one in this series, in other words, that time is equal to 3 times whatever the period is, or after 3 seconds. That first green circle has expanded out even more because, again, it's expanding out. The blue circle is now the blue circle at this point at 3 times the period should be equal to the size of the green circle at 2 times the period. And that red circle and at this point, a 4th beep is about to happen, or is happening. All right, questions about what this is representing? All right, so you have a source just sort of standing there, giving off these beeps, and the sound waves are being carried outward. So this dot right here is in the exact same place every single time. All right, so scenario number 2 is we're going to start out with an object at some particular location. So I can set it a little bit better. It gives off that sound wave at time is equal to t equal to 0, and that sound wave is released out into the wild. And so it's so big after 1 period, it's even bigger after 2 periods, and even bigger after 3 periods. So that first sound wave that's given off just starts expanding outwards. Like ripples in a pond when you throw a rock into it. The second sound wave is emitted, except the difference is between these 2 scenarios is I'm going to have this object moving to the right. So this is where it was when it gave off the first beat, but now it's going to give off the beat here. So when it gives off that second beat, it is closer to the right side of the first sound wave than it is to the left side. And so this will expand around this point right here where it's released. And then even bigger. And again, they're all supposed to be circles. And then since it's still moving to the right, it gives off the next beat even farther to the right. And so this one is centered around that point. And then it'll start the 4th beat. Close to there. So if these circles here, if the lines represent a high pressure, let's think back to when I was talking about representing how do we actually write sound waves, and one of the ways was doing it with circles where those represent the high pressure point. What can you tell me about a person standing here versus a person standing here? What will they sense differently?
It's going to be louder for the person on the right.
Is it louder? It probably will be. I was not going for that one, but yeah, they're not traveling as far. Okay. What else?
You said it was related to the pressure, so would the pressure be higher?
The pressure should be roughly the same as before. It might be a little bit higher because you're closer to the sound source, and so it might be a little bit louder.
the left would, like in that middle one, only hear that first community.
Why wouldn't they hear the second one?
Well, it looks like it would come at a delay compared to the guy on the right.
Okay, I'll buy that.
Yeah,
So the person on the right is getting hit more frequently
yes.
than the person on the left. All right, I'll buy that. So if you get hit by sound waves more frequently, how do we sense that?
Vibrations?
Say it again?
Vibrations?
Well, we're gonna sense it by vibration either way. Let's change the thought here for a second. Before I was sort of picturing once per second, in which case you get this beep, beep, beep. But now picture it happening 440 times a second.
It all becomes just one sound.
Okay, so how is this person perceiving the sound versus that person? If this person is getting hit more frequently,
They would be hearing it, the person on the right would be hearing it as more of a one sound than the person on the left.
440 hertz, they're both going to hear it as one sound, but there is going to be a perceived difference. And I'm pretty sure all of you have experienced this before.
Is
What do
the
you-
one on the right gonna hear it first?
No, they actually would, if they are equidistant from where the object was to begin with, they would hear it at the same time. Assuming they're standing still. That's the intent of the drawing, perhaps not the way I actually drew it. If you're hit by these high pressure waves more frequently, or more often, either way, think back to the vocab words. Let's think about it this way. You're standing on the side of the road, a car's coming towards you. Or can you tell if a car passes you? Based upon sound alone.
Yes.
How?
I wanna say it has something to do with the air.
Well, yes, it does. If there were no air, you would not be hearing them.
But wouldn't it be like vibrations then, like, cause of the sound waves hitting you?
I think part of it could just be my perception. When you say vibrations, I'm picturing the whole body sort of shaking.
What?
And not necessarily, and that potentially just,
Like
Me.
reverb, I guess, like.
say it again?
Like reverb, like, you know, when you're talking to a piece of paper, it starts like,
But what part of our body is most sensitive to these pressure waves?
eardrums.
Yeah, the eardrums. So let's talk about it in terms of hearing.
Oh, okay.
Because that's what, when you said vibrations, I was picturing, the body shaking. And like, let's concentrate solely on the eardrums. How will they be hearing these differently?
Is it the frequency?
Thus, he's going to be hearing it more frequently, or hit more frequently. Yeah. The person who is hit by the pressure waves more frequently is going to hear a higher frequency. When a car passes you, you get that. It's a higher frequency as it comes toward you, it's a lower frequency as it goes away. That's the Doppler effect. Now, if it's just a single beep, and it's a very quick beep, you actually would hear you would hear a difference in the frequency there, but it is not as stark as if it were hitting your eardrum so rapidly that your brain doesn't have a chance to process it as different sounds, but processes it as one sound. So as source and receiver get closer to each other, you get a higher frequency than if they're going away. Just some quick math. So the observed, this is for observer, or observed. The observed frequency is equal to the source, this is for source, the source frequency times a fraction. So this would be speed of sound, and I'm just going to use the letter C for speed of sound. And then speed of observer, speed of source. Now, whether it's plus minus or minus plus depends on if it's going to be a higher frequency or a lower frequency. And I've seen complicated charts. Just think through it. All right, they're getting closer to each other, so it should be a higher sound. So to make the frequency higher, to make this fraction more than 1, if they're getting closer to each other, it means I would subtract on the denominator or add on the numerator. So car, horn, let's just make it 400 hertz, traveling at 30 meters per second. Speed of car, 30 meters per second. Observer, standing on side of road. Observer, we'll just say speed of the observer is 0 meters per second.
Is the second one speed of car?
Yes, it is. So what will the person hear? Well, what the person in the car hears is 400 hertz. Because if you lay on the horn while you're driving, that horn is traveling the exact same speed you are. You're with each other. So relative to each other, there is no speed there. So the source is 400 hertz. Speed of sound, we'll just go with 340 meters per second. The observer is not moving, so plus is 0. And then 340 meters per second. Since the observer, it's heading, I didn't state that explicitly, so heading car, wow, my handwriting is horrible today. Car is heading toward the observer. So since the car is getting closer to the observer, the observer should hear a higher frequency. And so we want to make the denominator smaller. And if you get it wrong, if you think, all right, I know it's a higher frequency, you go through the math, you end up with a smaller number than 400, you then go, oh, oops, I guess I did the wrong sign. So 400 times 340 over 310, and you get something. If someone be kind enough.
438.71.
438.71. Okay.
Is it just hertz?
It is just hertz. Because the speeds in our fraction here all cancel out. The meters per second cancel out.
Yeah.
Let's change it around just slightly. See how much of a difference it makes. This time, car not moving. Observer heading toward car. At 30 meters per second. So this is sort of the first scenario here, over here, except this time the observer is running towards the car. So they're still gonna hit these high pressure waves more frequently because they're running into them. And so what the observer senses is that 400 hertz. And then our fraction of 340, again, you're hitting it more frequently, you should hear a higher frequency, so we're gonna add to the denominator 340 plus 30 over 340 plus 0, because the car is sitting there. And so this is 400 times 370 over 340. And so there's a little bit of a difference in the frequency that they're hearing in the two situations. And that's just the way the physics works. In 133, 151, and 251, we would derive this formula, but I will not subject you to it.
So why is the 30 on the top in one and on the bottom in the other?
Because it really depends on which one's moving. Because in the first situation right here, the source of the sound was moving, and in the second situation, the observer was moving.
Okay. So it's positive if, like, you know, you add 30 if it's moving towards the source?
Yeah, so if their source and the receiver, however it's happening, if they're getting closer to each other, you get a higher frequency, which means I'm going to add in the denominator or subtract in the, add in the numerator or subtract in the denominator. Either one is going to make the fraction higher. And if it's the observer that's moving, that affects the top, the source affects the bottom. I don't know if I got to the heart of your question, but
Yeah.
okay. Other questions right now?
So, just, I wanna make sure
Yeah.
I completely understand this. So if the observer was moving away from the sound, it would be a subtraction on the top and an addition on the bottom.
Is the car moving or just the observer?
The observer.
If the observer is moving away, then you will subtract on top.
Okay.
And the denominator is just gonna be 340.
Okay, right, okay, just wanna make sure I was doing that correctly.
All right, and as absolutely incredible as those drawings are, let's do something that's a little bit more professionally done. If I can find the remote on the floor. Anyone have, oh, there it is. Well, let's hope that something's gonna start popping up there. Does it sound any different?
There's a green light on.
Give it a little bit more time to show up there. We expect something to show up by now. Pardon? Now it's blinking. I will take that as an encouraging sign. There we go. By the way, YouTube reserves the right to put ads on anything. To my knowledge, they put no ads on any of my videos. Have any of you watched any of my videos and seen an ad? Okay. If Joanna, could you kill the lights, please? Thank you.
The Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you, and a car drives past you very fast. As it does so, it honks its horn because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look out your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does it mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves means a redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence for the Big Bang and an indication that the Earth might get very lonely in the distant future. Thanks for watching this video. Let me know if you got something out of it. Bye.
And I assume I have to edit that out of things that I post. There we go. So you can see from that dead-on representation in still frame. Now, let's take it one step further. Oh, questions before we take it one step farther? So we'll go to the absolutely spectacular frames again. So let's alpha beep here. And now the sound wave goes on and expanding. We'll pretend those are circles. Except this time, instead of just traveling within the bubble here, it's now going to travel faster than. So the next beat gets off at that point right there. Red, so just ahead of the wave. The last one right there. What's happening here? What does it mean when these waves are overlapping like that?
Both of the sounds sound as one?
They do. What does that mean? Because there is a difference between this, I mean, that's a whole lot of different waves, but we treat that as still a single sound. How's that different from this?
Is that when it like breaks the speed of sound?
Yes. And?
There's like the boom, like you don't really hear anything.
And you were saying?
I said you can't hear it.
Oh, you can definitely hear it. Remember that these circles represent high pressure. In this situation over here, the high pressure doesn't overlap. We just process it as a single sound. But here, high pressure is overlapping. So if you think about a loud sound, boom, and now double the volume, we get this incredible buildup of pressure waves here. Now, if it's letting out a continuous sound, we don't have these discrete circles like this.